Thanks for the introduction. So I'm Radek. I'm from Brno, Masaryk University, and I will present work with my two colleagues, Tomáš and Jaroslav. So the topic of our, can you see in my slides, all slides? Okay, thanks. So high-level overview of our work. What we do is we study a student model called Additive Factors Models, which is quite widely used student model. And we explore its robustness, generalizability to new settings, and its simplifying assumption. So we do not do any proposal of a new model, although we still do some slight variations, but mostly we take a model that people used before, and we study how robust it is, whether it is generalizable, and so on. And the main message of our work is that more caution is needed with respect to some of the previous work. So that's a high-level overview of the type of the work that we are doing. Before I start with the work itself, here I have some high-level overview of student modeling of different applications of student models and how the AFM model that we study fits in. So at first, what we consider are only models of cognitive knowledge. So we do not study modeling of affect and such things, only knowledge. And the typical application of student modeling of knowledge looks something like this. We have a student model which takes data about the student item interactions, and based on this data, it tries to estimate the knowledge of students. And this estimate of knowledge can be used in several different ways. It can be used for instructional policy, for estimating for example, for master learning, or for recommending suitable items for students. Or it can be used in this so-called inner loop for providing hints to students, and so on. Sorry. And also we can use estimated knowledge in open learning modeling, in line dashboards. And finally, and this is the topic of our work, of the typical application of AFM model, we can use the outputs of the model for some actionable insight, which is taken by the human and used, for example, to change the domain model or to create new items. So the AFM model is typically not used in these online loops for automatic intervention, but for these human in the loop interventions for getting actionable insight. So a brief summary of the model. The additive factor models belongs to a family of so-called logistic models, which somehow predict the probability of correct answer by a logistic function. It uses multiple skills defined by so-called Q-matrices. And as I said, it's a model that has been used in recent years in many studies. So for the Q-matrix, that's the important part of the model. There's a matrix, and here I have a specific simple example. So here we have several items from mathematics, several skills, subtraction, addition, multiplication, parentheses, and so on. And the Q-matrix specifies which skills are relevant to which concept. So this is something that's used in the model. This is like the mathematical description of the model. It seems pretty complex with a lot of letters, but I will explain rather on a simplified figure. The main idea of the model is not very difficult. It's just some linear combination of item and student parameters, and then we apply a logistic function to get a probability of correct answer. So I will not go through all the letters. I will just provide an illustration on intuitive illustration on an example. So the model assumes some student prior skill, a single one-dimensional parameter of the student. So that's our starting point. Then for each skill that's relevant to the item, here we do some updates of the skill. So here in my simple example, I assume an item which is relevant to two skills, blue skill and orange skill. For each skill, we have a skill easiness parameter. In my example, the blue skill is easy, so the skill easiness is positive, so we we add this to the student's prior skill. The orange skill is difficult, so the skill easiness is negative, so we decrease the estimate. And then we take into account practice opportunities. So let's say that for the blue skill, the student had one practice opportunity. So we increase the estimate by another parameter, learning rate. And for the orange skill, the student had 3 practice opportunities. So we increase by the orange learning rate 3 times. And finally, we apply the logistic function to produce a probability of a correct answer. So that's the output of the model. So that's the basic idea of the IFM model. Now, one of the points of our work is to explicitly describe the simplifying assumptions behind the model. Of course, all models are wrong. All of them have some simplifying assumptions. So the fact that a model has a simplifying assumption is not necessarily a problem, but we believe that it's useful to have an explicit list of the simplifying assumptions, because if we ignore the fact that there are simplifying assumptions, we can sometimes this can lead to misleading conclusions. So here the assumptions are discussed in more detail in the paper. I will just summarize the main one. For example, one of the assumptions is that the learning is linear. With the number of opportunities on the logit scale, the estimated skill increases linearly, which is, of course, simplifying. Also, the model does not take the observed answers of students into account. We just take the number of practice opportunities into account, and we do not take into account whether the answers were correct or incorrect. There are extensions of the model like PFA, performance factor analysis, which take into account, but the basic AFM model just takes the number of opportunities into account. Also, the model considers only binary outcomes. It ignores other data about student performance like response times, or in the case of wrong answers, whether the answer was a common wrong answer or whether it was some obscure wrong answer, which can be also informative. Also, the Q matrix is just binary, which is, for example, in this example, is quite natural. But for example, in programming, which is our case study, it may make sense to have some of the constants non-binary. For example, there is a while loop required for the solution, but maybe it's not completely necessary. So maybe some value between 0 and 1 would be more meaningful. Also, the model uses so-called compensatory model of skill. Let's go to our example. So in this case, for example, let's say that the student practices only the blue skill many times and does not practice the orange skill at all, which in this model would lead to, after some time, to prediction of perfect answer, even though in reality the item may require at least some knowledge of the orange skill and some practice of it as well. And also, the model ignores the difficulty of items and biases in data like fixed ordering of items, which is something that we explore in our case study. Then, before I go to the case study, another thing is our learning curves, which are typically used for analyzing the model. The basic idea of learning curves is simple. We just plot the error rate as a function of number of attempts. And typically we would like to see something like this, that the error rate goes down as students have more and more practice opportunities. With the AFM model, the problem is that the learning curves can be constructed in several ways. The construction of learning curves is complicated by the fact that each item is relevant to several skills. So it's not easy to say how we should compute the error rate and how we should count the attempts when there are several skills per item. In the paper, we describe several types of learning curves which make sense for the model, from empirical, which is based only on the observed data, to idealized, which is constructed using the fitted model, and some simulated attempts. And all of them make some sense. I will not go into the details of these curves because it's a bit technical. You can find in the paper. I will just illustrate some illustrations on simulated data. So we have constructed a similar illustration using simulated data, which shows the differences between these curves. Depending on the way we construct the learning curve, we can get quite different curves. And also it shows some problems with the learning curves. This example is constructed using a simple simulated setting where we assume 2 skills. One of them is easy, the second one is difficult. We have just 15 items. First 5 of them are related to skill 1. The next 10 are related to both skill 1 and skill 2. And we have several simulated students which are learning according to the model. So these are kind of optimal students for the model. And we consider their learning in the random order and in fixed order with some small probability of skipping. In this way, we try to simulate something that we observe in our real-life learning systems, that typically students proceed through items in some fixed order. And these are the results of the simulation, which show one thing is the difference between the empirical and the idealized curve, that each of them looks quite different on the graph. And what's more particularly important, in the case that the students proceed in some fixed order, we can get a really strange, particularly the empirical curve can look really strange. It doesn't look nicely as we expect, but something like this, because here the fifth item, sixth item are related to the more complex skills, which causes this deviation in the data. With the idealized learning curves, we can smooth this out and construct the nice learning curve, but only thanks to the fact that the assumptions of the simulation correspond exactly to the model. So these are the learning curves. And now I will go for the case study. Before our case study, here I was a brief summary of the typical application of the AFM model, how it was done in previous papers. As I said, there are more than 10 papers that describe different applications of AFM to different types of data, math, and typically from mathematics, but also from other domains. And the typical application is that the researchers take the data, they feed the AFM model with several Q-matrices, typically of different granularity. Then they take the Q-matrix with the best fit. They say that, okay, this seems to be the best definition of skills for this domain. And then they analyze the learning curves of the best fitting skills, and to find out whether some of the skills are maybe specified and so on. Typically, people analyze just one type of the learning curves. This is, of course, simplified summary of the previous research, but the base, many papers somehow fit this framework. So now, our case study, what we have done is we have tried to apply the AFM model to programming, which is a domain where it was not used so much so far. And we try to see whether we will get any meaningful results. And we try to be careful with different methodological choices to check whether the model is robust and provides the same answer depending on the choices that we make. So for our data, what we use is basic introductory programming, quite common approach using block-based programming for kids. The size of the data is about 80,000 items, 3,000 students. We have 80 different items, 80 different programming problems that students solve. The system that we use is publicly available. It is even open source. And also the data that we use are available, and they are quite nicely described by one of my co-authors in this paper. So if anybody wants to play with programming data, you are welcome to try it. The questions that we studied concerned, as I said, we were not interested that much in developing a new model, but rather in trying how the existing model is applicable in new settings. So we studied generalizability, how well the model works in this domain, whether we can use it to find good Q-matrices, whether the learning curves provide insight. And we also tried to explore the robustness of the results. We have tried the experiments with different methodological choices, for example, different cross-validation settings, to check whether the choices that we make during the evaluation influence the results that we get. In the evaluation, we used 4 Q-matrices of different granularity, from the most fine-grained to the most Q4 is most coarse. That's just 4 programming concepts. The first Q-matrix has many more programming concepts and also some skills corresponding to the specific aspects of the microword that we used. In model comparison, we used the AFM model. This one is the basic AFM model. We also tried a variant without the alpha parameters, without the student skill, because preliminary experiments show that it is not that much useful in our setting. And we also tried an extension with item difficulties, because this turned out to be quite important in our setting. And we compared the model performance to some simple baseline like global average performance and item average. As I said, one of our aims was to explore the robustness, so we tried explored how different methodological choices in the evaluation influence the results. So here I have some graph corresponding to these evaluations. For example, we explored the effect of data filtering or of cross-validation setting, how different choices of cross-validation or of data filtering, for example, if we filter out students who answer only a few questions which are probably noisy, if this influences the result. I will not go into details of these experiments because the basic result here was that the choices influence the values of the metrics, but they do not influence much the ordering of the models. So these choices, it turned out that the results are quite robust with respect to these choices, which is good to know, but nothing really surprising here. I will discuss it with more detail. This figure, here we have comparison of the models with respect to several metrics. Again, we have tried to explore how the results are influenced by the choice of performance metrics. And there are slightly. There are some differences that we discuss in the paper. Here, for brevity, I will discuss just results for root mean square error, which is one of the most common metrics that we prefer to use for evaluation. And here we have the comparison of our models with the baseline. The black line is the global average, the very simple baseline. The gray one is the item average, slightly more clever baseline, but still something simple. And here, these are the models, different variants of the models, sorted from the most granular Q-matrix to the most coarse Q-matrix. And as the basic AFM model, the one from the literature, is the green one. As we can see, the green one is better with the more granular Q-matrices, but even the best result for the basic model is worse than the item averages. So it's the model is worse than something very simple. Only when we have extended the model to take the item difficulties into account, then it is able to achieve better results than the baseline. And here we have some learning curves. These are the learning curves for the basic model, for the one that's used in the literature. So if we have just used the standard approach in the literature, and we would just fit the model with different Q-matrices, this is basically what we would end up, these learning curves, which are very bad. The fitted curves go upwards, which is something that we do not want to see in the learning curves. We want the learning curves to go down because we want to see the failure rate going down with number of attempts. But for the basic model that we fitted, they go up. Our explanation is that this is because of the ordering bias in the data. Most of the students proceed through the examples in the same order. So for example, when a student solves 8 problems with a while loop, this problem is typically much more difficult than the first or second one in the sequence, and hence the failure rate goes up. And this is something that the basic AFM model does not take into account, and it can lead to this wrong, bad-looking learning curves. So, to summarize, the main point of our work is that the studies that are using the additive factor models need to be more conscious, because the AFM model has many simplifying assumptions which may not be satisfied in practice, particularly for our domain in programming. Many of the simplifying assumptions are really not satisfied, and if we just try to use the AFM model out of the box, like in the same way as other people have used it, and we would not be careful with the interpretation and with exploration of the results, this could lead to possibly misleading conclusions. And as a basic precaution, based on the experience of our experiments, we believe that the basic precaution should be the comparison of the model with some really simple baselines, like the item average predictor, which is something that is missing in most of the previous work. So that's all for me. I welcome your questions either now or later electronically through mail or discussion board.